All right, so now that we know how to do limits of vector value functions, the next thing is to start talking about derivatives. So if we were to define the derivative of a vector valued function, it looks like this, which should look familiar to you. The limit as delta t approaches 0 of r of t plus delta t minus r of t over delta t. This is exactly the form of the limit of a real valued function. Replace r's with f, and essentially you have your derivative of a real valued function. So that's going to tell us that these really shouldn't work all that different than what we've looked at already with real valued functions. So ultimately, if I take the limit of a vector value function that, say, is made up of these three components, f of t, g of t, h of t, which remember are real valued functions, then the way we do that is essentially to take the derivative of each real valued function. This prime notation is in the wrong spot. The prime should actually be there, there, and there. It should not be on the t itself, so let's erase that. All right, so you take the derivative of f of t, g of t, and h of t, and that's how you're going to take your derivative function. And if you were to take the second derivative or third derivative, it would pretty much work the same way. So in this case, if I wanted to take the derivative of r of t, knowing r of t is made up of these three functions, the derivative of r of t should be the vector 3t squared. That would be the derivative of 1 plus t cubed. And then it should be the derivative of the j component, which in this case we're going to need product rules. So we're going to say e to the negative t minus t e to the negative t. That would be using the product rule, where we took the derivative of t, then the derivative of e to the negative t. And then the third component would be the derivative of sine 2t, in which case we should get 2 cosine 2t. So here is our vector value function's derivative. And I wrote it in component format. I could write it in IJK, which is how the original vector was written. It really doesn't matter. But it's fairly simple to take the derivative of vector value functions, again, if you know how to do the derivative of real value functions. So you got to have your derivatives down for this to be able to work. Right, so this animation gives you the idea of what's happening with the derivative function. So, when we looked at the derivative as a limit, the limit as delta t approaches 0 of r of t plus delta t minus r of t all over delta t. It essentially had to do with this concept that we saw back in Calc 1, where the secant line was turning into a tangent line in a way. In this case, the secant vector turning into a tangent vector. And what you basically do is you have two vectors. You have this vector here, and then you have this vector here. This one would be, say, r of t, and this would be r of t plus delta t. And what we want to do is we want this vector to get closer and closer to this vector, so we get this, this, this. Why? By shrinking t, delta t, down to 0. So what we're doing is we're making this vector get closer and closer here, which essentially moves us along the curve. And then we look at the vector between this point and this point here, which we can call the secant vector. And that secant vector, as t gets closer to 0, scales down to become essentially this final blue vector, which is the tangent vector at this location. And if you remember back to Calc 1, that was very similar to the way we found the slope of the tangent line. So that brings us to the idea of what is the derivative. Well, the derivative of a vector value function is another vector value function. Specifically, what vector value function? Well, something that we call the tangent vector. So here we go. We got r prime is denoted as called the tangent vector. Okay, it's a vector that's tangent to the curve at a particular point. So it's tangent to the curve by r at point P. R prime of t exists is one of the requirements, because obviously for the tangent vector to exist, r prime has to exist. We also look at r prime to not be 0, so it's not the 0 vector. And what we're basically going to get is a vector that's parallel to the tangent line. And so if we were to look at some curve, if we take maybe that last example, and you look at some curve, let's say this helix curve, and we're looking at this point right here, the tangent vector right there would be this vector, and the tangent line would be the line that's tangent to the curve there. And if my drawings were accurate, that vector and that line would be parallel to each other. So then if I said, let's write the equation of this tangent line, what do you need to write the equation of a line in 3D space? Well, you can't just write a single, you have to write a parametrization, but you need a vector parallel to the tangent line and a point on that tangent line. Well, having that tangent vector in that point, you have everything you need to answer, say, a question like this, where we want to write the equation of the tangent line. The tangent line to C at P is defined to be the line through P parallel to the tangent vector. So we would have to find the tangent vector at this location. That would give us our vector parallel to the tangent line. We'd also have to find the point that we're located at with this t value, and we could write the parametrization, and it has to be parametrization because this is happening in 3D space with this, say, this helix curve or whatever curve this ends up being. It's clearly a 3D curve, ijk. So first thing we would do is we could find the derivative. So r prime of t can be easily found by doing the derivative of each one of these, which should be simple enough. 3t squared plus 1i plus, this would need product rule, so we'll say e to the negative t minus t e to the minus t, that's my j, and then we have 2k. So there's my tangent vector at 0, I don't know how that happened, but let's say at t equals 0, we would have to find r prime of 0, and that would simply just be 1i plus, this would be e to the 0 times 0, so we're going to get 1j and then 2k. So that's the tangent vector at that specific location. So that's the parallel vector when t equals 0. Remember, t equals 0 gives us a specific spot on the curve. This is where t equals 0. So we're finding the tangent vector there. And then the next thing we want to do is find that point, though. What point does this t value get me to? Well, remember, if a vector starts at the origin, right, if we start at the origin, say 0, 0, 0, and we're pointing to some particular point, the components of the vector, let's say a, b, c, would be the same as the components of the point a, b, c that it points to. So I just need to know what vector this is, okay, in terms of r of 0, because r of 0 would be this vector that starts at the origin and creates the point on the curve. So I want to find r of 0, and r of 0 would be the vector 2i plus 0j minus 3k, and all I'm doing is plugging 0 in for t here. And that's the vector, so that vector points to the point 2, 0, negative 3. So this is the point, this is the location of the r prime of 0 when t equals 0. So now we have our point, we have our vector, and using those two things we can do the parametrization, which would be simply the tangent line would be x equals x1, which would be 2, plus at, so plus 1t, y equals 0, plus 1t, that would be bt, and z equals -3 plus 2t. Remember, a, b, c, x1, y1, z1. So this is the parametrization of the tangent line when t equals 0 to this function. And so this picture just gives you an idea of what I was just showing. Now this orange curve is not the curve we were just dealing with in that last example, but it gives you the idea of here's a particular location. We would have a vector that created this curve, or let's say a vector value function that created this curve for different t values. This would be the t value, say at 0. We would get to this location. I would find the derivative at 0, and I would get this vector. So that vector right there would be r prime of 0. And then I want to find the equation of this line that is tangent to the curve at that point. So parallel to the tangent vector at this particular location on the curve. And again, that's similar to what we did in the last example. Now that last example wasn't this orange curve, but this orange curve kind of describes the same idea of what was happening throughout that last problem. Now we just have a few things we need to discuss real quick that'll come up later. One has to do with the concept of what we define as a smooth curve. So this says the parametrization of the curve represented by the vector valued function, which is essentially the way we represent curves in 3D space, right? We have to do it through vector valued functions. It's the only way we can represent curves in 3D space. So let's say this parametrization represents a curve in 3D space. We'll say that that curve is smooth on an open interval I if the derivatives of all the individual component functions are continuous on that interval and the vector value function isn't the 0 vector for any t value in that interval. So we just define that as a smooth curve. So it's sort of a continuation of, or it's probably the wrong word to say, but a variation maybe would be the better word of continuity. A curve being a continuous curve, that the components of the vector value function are continuous and the whole vector value function itself doesn't give you the 0 vector. That's just, there's a theorem we'll talk about later in the semester that requires all the curves in the theorem that we use within the theorem to be smooth curves. All right, so then we have a couple of properties we want to talk about. So how do some of these algebraic properties of vectors relate to derivatives? So we have derivative rules that relate to real valued functions, but we don't really have derivative rules that relate to vector valued functions. Like how do we take the derivative of a sum of two vector value functions, a product of two vector value functions? Well, there's different kinds of products. Constant multiple rule. So we have to redefine some of this stuff, and we won't take very long to do so, but it just needs to be defined. And mostly what happens is it follows the same rules that happen for real value functions. It really does. There's just a few things that we have to talk about, because if we were to do some proofs with some of the things as we move forward, we would need to know how this works in general between certain vector valued functions. So first one is the constant multiple rule. If I have a constant multiple times a vector value function, one thing I could do is I can just multiply that constant multiple in first and then take the derivative and not worry about any of this. But let's say I don't want to multiply that lambda into the vector function. So I want to leave it out on the outside, but I still want to take the derivative of the whole thing. Well, this says that I can pull lambda out of the whole derivative, just take the derivative of the vector value function itself, and then multiply lambda in. And so that's the same as your constant multiple rule, right? The constant multiples can come outside of derivatives. And whether it's the derivative of a real function or a vector value function, it works the same way. And here's the sum and difference rule. If I have two vector value functions added together or even subtracted, and I want to take the derivative of the whole thing, well, one thing I could do is add them together first and just do that computation using my how to add two vectors together and then take the derivative. But let's again say I don't want to do that. What I could do is if I want to take the derivative of this sum or this difference, this is telling me I could take the derivative of each piece separately and then do the sum. So I could split apart sums and differences, which works the same way with real value functions as well. You know, the derivative sum is the sum of the derivatives. Okay, now we get some products. There are three different products we're going to look at. W of t is a real valued function. W of t is a real valued function. Notice in the notation it's not bolded the W, which tells me it's a real function. There's a bolded letter on the R of t because R is a vector valued function. So if I have a real value function times a vector valued function, and I want to take the derivative of that, again, what I could simply just do is I could multiply these together first and then take the derivative. And the question is, well, how would I do that? So let's say, I don't know, I have x squared times cosine t sine t log t. So here's a vector valued function, and here's a real valued function, and they're being multiplied together. Well, I do it a lot like I do the constant multiple one. This would multiply in here, here, and here. So you can multiply a real value function times a vector value function. It's definitely possible. And you just do it together. In which case then, you know, how would I take the derivative of that? I would take the derivative of each piece. But this says if you didn't want to do that, what you could also do is you could essentially apply the product rule. You think of these as two functions. You got to take the derivative one at a time. So this says I'll take the derivative of r first, and then w is going to be on the outside of that, so w stays unchanged, plus r times the derivative of w. In this case, r stays unchanged, and w would take the derivative. So one at a time with the product rule, adding them together. Remember, w is a real valued function. So you can apply that product rule to this type of product. But there's other products we can do. We can multiply two vector valued functions together. But since they're vectors, vector valued functions, but vectors, there's two types of products, dot product and cross product. So the question is, all right, how does this work? Well, again, I could just do the dot product between these two and then take the derivative, but I could also apply the product rule. I could take the derivative of one at a time times the original plus v times the derivative of r of t, and add them together. Just apply the product rule to that. It works just as well. And cross product, same thing. I could do the cross product first, and it's a cross product between two vector value functions, which isn't ideal, but you can still do it. It's just you have functions in each component instead of constants, but you could do the cross product. And then I could take the derivative, or again, I could do this. Now, this is the only one that order is really important because, you know, cross product is not a commutative operation. So if r was in the front spot of the cross product and v was in the second register of the cross product, that has to remain in this form here. So here I'm going to take the derivative of v of t, and I'm going to cross it with r of t, but I got to keep the order preserved. So v is in the second register still, but I'm taking the derivative of v. And then here, I'm going to take the derivative of r and not v, but r still stays in the first register. Even though it's the derivative of r, it still stays in the first register. And then v is in the second piece of that cross product. And we're adding them together. So it still looks like the product rule, and still works where you do one at a time, but here the order does have to stay specifically in that way. Here I can mess around with this all I want and I'm still going to get the same answer because dot product is commutative anyway. And then finally we have the chain rule, in which case I have a function inside of a function. But notice I have a real value function inside of a vector value function. And first off, how does that work, right? So if I said I had w of t to be, I don't know, let's say x squared again, and I had r of t, which is my vector function, to be cosine t, sine t, log t. How would I find r of w of t? How would I do this? Well, I'd have to plug this in, x squared in for t, right? So I would have to say, what's r of x squared? So the way I do that is I'd have to plug x squared in for essentially each t, and not x squared, sorry, it would have to be t squared, obviously, because it's a function of t. So I'd have to plug t squared in every time I see a t. So then the composition would just be cosine t squared would be the first component, and sine t squared, and log of t squared. So that's how you take a function, a real function, and plug it into a vector value function. You cannot do the composition of a vector value function inside of, say, a vector valued function. I can't do the composition of that. It doesn't make any sense. But I can do real inside a vector. So, what it says is I could do that first and just get this vector here and then just take the derivative of that. That's possible. Or I could apply this chain rule where I take the derivative of the outside, which is r prime, w of t, the inside stays unchanged. Then that vector gets multiplied by the derivative of w. So again, chain rule. Derivative of the outside, inside stays the same, then times the derivative of the inside. So this is how you would do it, for just random r's and v's. If you had specific vectors, most likely what you would do is you would just apply the operation first. It's usually simpler just to do these operations first, get the answer, and then take the derivative of that, as opposed to trying to do all this out. But just so you're aware that these would be some of the properties if you did want to apply some of those derivative rules to vector valued functions. This is how they would work. So the big one is there's really 3 different product rules depending on what kind of product you're doing. And then we have integration. So with integration, what we want to do is go backwards from derivatives. So in order to take the derivative of a vector value function, I do it component by component. Well, integration should work the same way. If I want to take the integral of r of t, it should be the integral of each component separately. And whether it's a definite integral like this or an indefinite integral like these, it doesn't really matter. You do it component by component. Now, each one of these is its own integral. And since these are indefinite integrals have a constant of integration. But the constant of integration for this integral is not necessarily the same constant as the constant of integration for this integral or this one. So we would have to denote it that these are separate constants, not one constant that's the same all the way through. With definite integrals, these end up just being a constant value in the end, so I don't have that issue. You plug a and b in and subtract b minus a for the antiderivative, but so we don't have that issue for the definite integrals, but the indefinite integrals, we would have to denote the different c values. But again, just do it piece by piece. So for this example, this is an indefinite integral. In order to do this, I'd have to know 3 integrals. One, the integral of 2 cosine t dt. Then I would have to know the integral of sine t dt and the integral of 2t dt. So the first one is easy. It would be 2 sine t plus c, right? And again, indefinite integrals. But I'm going to say c1 because that c is going to be different than my next one, which will be minus cosine t plus c2. And the last one would be t squared plus c3. Again, because this constant is not the same necessarily as this one is the same as this one. So then the integral of that vector valued function, say 2 cosine t I plus sine t j plus 2t k dt would be the vector 2 sine t plus c1 in the first register, in the first component, minus cosine t plus c2 in the second component, and then the third component I'll have to write down here because I'm out of space, t squared plus c3 in the third component. So I, j, k. It's still another vector, right? The integral of a vector value function is another vector value function, but we have to do it component by component, and the constants of integration just have to be denoted as different. I have seen some people just write the integral of each component, so there's the integral of the first one, integral of the second one, integral of the third one, and then throw plus c at the end. But that doesn't really make any sense because now you're saying you have an integral, you have a vector plus a constant, and you can't actually add vectors plus constants. Like it's just not doable. So it doesn't really make a lot of sense notation-wise. So I don't do that. Put the plus c in each one and make sure it's c1, c2, c3. Other than that, there's not much to this as long as you know how to integrate. We could do it with a definite integral as well, in which case if I want to do this definite integral, I have the integral from 0 to 1 of, let's write this as t to the 1/3 dt, that's my I, plus the integral of 1 over t plus 2 dt, and that's going to be my j, plus the integral of e to the t dt, it's going to be my k, and again, these are 0 to 1, 0 to 1. So t to the 1/3, I have to add 1 and divide by, so that's 4/3, so 3/4 t to the 4/3 between 0 and 1. Again, that's my I. The next one's going to be log of t plus 2 between 0 and 1. That's going to be my j. And the last one will be e to the t between 0 and 1. That's going to be my k. So plug in 1 and 0 for each one. So I plug 1 in here, I'm going to get 1, so I get 3/4. Plug in 0, I get 0. I subtract. That's my I. And here I'm going to get log of 3 minus log of 2. When I plug in 1 and 0 in for t, that's going to be my j. And here I'm going to get e to the 1 minus e to the 0. That's my k. So in the end, I get 3/4 I plus, I could write this as log of 3/2. Since they're subtracted, I can do division. That's my j. And then my last one would be e minus 1k. So there, that's my definite integral of this vector value function between 0 and 1. No c's, again, because it's a definite integral. But it's just a matter of integrating each component. So this, again, should be not a big deal to do as long as you know how to do integrals of real valued functions.